Welcome! In this session, we'll explore problem number 1866, titled Number of Ways to Rearrange Sticks with K-Sticks Visible. This problem challenges us to think critically about permutations and visibility constraints, making it an exciting topic to tackle. Let's dive in. In this problem, we are tasked with arranging n uniquely numbered sticks, each with a specific height, in a line. A stick is considered visible if there is no taller stick to its left that obstructs the view. Our goal is to determine the number of ways to rearrange these n sticks such that exactly k sticks are visible. Since the number of possible arrangements can be very large, the result must be returned modulo 10 to the power of 9 plus 7. The input consists of two integers, n, the total number of sticks, and k, the number of visible sticks. The constraints are that n can range from 1 to 1000, and k must satisfy 1 equals k equals n. The output is a single integer representing the number of valid arrangements, modulo 10 to the power of 9 plus 7. To understand the problem better, consider the first example where n equals 3 and k equals 2. The output in this case is 3. There are three possible arrangements of the sticks where exactly two sticks are visible. For instance, in the arrangement 1, 3, 2, stick 1 is visible because it's the first stick, and stick 3 is visible because no stick to its left is taller. Similarly, 4, 2, 3, 1, sticks 2 and 3 are visible, and 4, 2, 1, 3, sticks 2 and 3 are visible again. Now take another example with n equals 5 and k equals 5. Here, the output is 1 because the only possible arrangement is 1, 2, 3, 4, 5, where all the sticks are visible in increasing order. In the third example, we are given n equals 20 and k equals 5. The output for this case is a large number, 206085257, but it is returned modulo 10 to the power of 9 plus 7 is required. This example highlights the computational challenges of solving the problem directly due to the sheer number of possible arrangements, especially for larger values of n. The result demonstrates the importance of an efficient approach, as brute forcing all arrangements is impractical. Additionally, the constraints provided specify that n can go up to 1000, meaning our solution must handle large inputs efficiently. This is why the modular arithmetic and efficient computation become critical in solving this problem. Now, let's consider some key observations that simplify the problem. First, if k equals n, there is only one valid arrangement. The sticks must be in strictly increasing order to ensure all k sticks are visible. On the other hand, if k equals 1, the tallest stick will be the only visible one, while the remaining sticks can be arranged arbitrarily. These edge cases provide insight into the structure of the solution. For intermediate values of k, dynamic programming can be employed to calculate the number of valid arrangements efficiently by breaking the problem into smaller subproblems. This approach ensures that we can handle the constraints effectively while optimizing for performance. To solve this problem, we first considered a brute force approach. The intuition here is straightforward: generate all possible permutations of the n sticks and count how many of them have exactly k sticks visible. A stick is considered visible if it is taller than all the sticks to its left. For each permutation, we iterate through the sticks to verify how many satisfy this visibility condition. However, this approach is computationally expensive. Generating all permutations requires factorial time, O, n, and verifying each permutation adds an additional O, n, leading to a total time complexity of O, n. *n. The space complexity is also significant, as we need O, n, space for storing each permutation and the recursion stack during generation. This makes brute force infeasible for larger values of n, as the number of permutations grows exponentially. Instead, we turn to an optimized approach using dynamic programming, which allows us to efficiently calculate the number of ways to arrange n sticks with exactly k visible sticks. Now, let's delve into the dynamic programming approach, which is both practical and efficient. The key idea is to define a dp state, dp, n, k, to represent the number of ways to arrange n sticks such that exactly k are visible. To derive the recurrence relation, we make two key observations. First, if the tallest stick is visible, it must occupy the first position, leaving the remaining n1 sticks to be arranged so that k1 are visible. Second, if the tallest stick is not visible, it can occupy any position except the first. In this case, the remaining n1 sticks must be arranged with all k sticks visible, and we account for the n1 possible positions of the tallest stick. This leads to the recurrence relation, dp n k equals dp n1 k1 plus n1 asterisk dp n1 k. The first term corresponds to the tallest stick being visible, while the second term represents the cases where it is not visible. For the base cases, dp 0, 0 equals 1, since there's exactly one way to arrange 0 sticks with 0 visibility. For all n greater than 0, dp n 0 equals 0, as it's impossible to have 0 visibility with non-zero sticks. Similarly, dp n k equals 0 for all k greater than n, as we cannot see more sticks than are available. Using these observations, the dp table is filled iteratively, and we compute results modulo 10⁻9 plus 7 to handle large numbers efficiently. This gives us a time complexity of O n squared for filling the table and a space complexity of O n asterisk k. To further optimize space, we can use two 1D arrays, previous and cur, to store results for the current and previous rows, reducing the space complexity to O, k. The dynamic programming solution is chosen because it is computationally efficient and leverages the structure of the problem to break it into smaller, manageable subproblems. By focusing on the visibility of the tallest sticks, we can use the recurrence relation to compute the result iteratively, avoiding the exponential complexity of brute force. Compared to a combinatorics-based solution, which is possible but often error-prone and less intuitive to implement, the DP approach strikes an excellent balance between simplicity, correctness, and efficiency. It's easier to debug and extend, making it a practical choice for this problem. While brute force is infeasible due to its factorial growth, and combinatorics can be challenging to apply correctly, the DP strategy provides a clear and systematic way to solve the problem within reasonable time and space constraints. This makes it the ideal approach for tackling this problem efficiently. To solve this problem, we start by understanding what it means for a stick to be visible. A stick is visible if it is taller than all the sticks to its left in the arrangement. The task is to determine how many permutations of n sticks result in exactly k visible sticks. One straightforward way to approach this is through brute force. First, we generate all possible permutations of the n sticks. Each permutation represents a unique arrangement of the sticks, and we can evaluate it to see if it meets the visibility condition. To generate these permutations, we can either use a backtracking algorithm or leverage a library function like Python zittertools.permutations, which is efficient and easy to use. Once all permutations are generated, we'll move on to analyzing them to count the visible sticks in each arrangement. Now, let's look at an example to make things clearer. Suppose we have 3 sticks with heights 1, 2, 3. The total number of permutations is 3, which gives us 6 possible arrangements: 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. Once we have these permutations, the next step is to determine how many sticks are visible in each arrangement. To do this, we traverse each permutation from left to right, keeping track of the tallest stick we've seen so far. For every stick in the arrangement, if it is taller than the current tallest stick, it becomes visible. We then update the count of visible sticks and adjust the tallest stick reference. This process helps us evaluate each permutation to see if it satisfies the condition of having exactly k visible sticks. Consider the permutation 2, 1, 3 as an example. We start with a max_height of 0 and a visible_count of 0. As we traverse the array, the first stick is 2. Since 2 is greater than the current max_height of 0, it is visible. We increment the visible_count to 1 and update max_height to 2. Next, we encounter stick 1. Since 1 is less than or equal to max_height, which is now 2, it is not visible, and we make no changes. Finally, we reach stick 3. Since 3 is greater than max_height, it is visible. We increment the visible_count to 2 and update max_height to 3. At the end of this traversal, the total visible stick count 4, 2, 1, 3 is 2. If the desired k value for this problem is also 2, then this permutation meets the condition, and we include it in our count of valid arrangements. We repeat this process for all permutations, checking the visibility condition each time. There are a few key insights that arise from this brute force approach. First, visibility is determined only by sticks that are taller than all the sticks to their left. This means that shorter sticks to the right of a taller stick do not affect visibility at all. Second, while brute force ensures correctness, it becomes computationally expensive as n grows. Generating all permutations has a time complexity of O(n), because there are n possible arrangements. Counting visible sticks for each permutation requires traversing an array of size n, which adds an additional O(n) complexity. Thus, the overall complexity of this approach is O(n)*n, making it impractical for large values of n, such as n greater than 10. On the positive side, this method has minimal memory requirements, as we only need an array to store permutations and a few counters, such as visible_count and max_height, to track the visibility during evaluation. Finally, let's summarize the key operations and discuss potential optimizations. The main operations in this brute force approach are generating permutations, checking visibility, and counting valid arrangements. Generating permutations can be efficiently handled using backtracking or library functions, while visibility checks involve a straightforward traversal of each permutation. To improve performance for larger values of n, we can explore dynamic programming. For instance, we can use recursive relationships with memoization to calculate the number of valid permutations without explicitly generating them all. Additionally, we can prune permutations early during generation if they fail partial visibility constraints, reducing unnecessary computations. These optimizations make the problem more tractable for larger inputs, transitioning us from a brute force solution to a more efficient and scalable approach. This solution uses dynamic programming to efficiently calculate the number of ways to rearrange n sticks with exactly k sticks visible. The problem is solved using a recurrence relation that accounts for two key scenarios: placing the tallest stick in a visible position, and placing shorter sticks such that visibility remains unchanged. First, a 2D list dp is initialized to store intermediate results, where dp ij represents the number of arrangements of I sticks with j visible. The base case is dp 0, 0 equals 1, corresponding to an empty arrangement. The dp table is filled iteratively. For each stick count I and visible count j, we calculate dp ij using two terms. 1. dp I1 j1, placing the tallest stick in a visible position, which increases visibility. 2. dp I1 j I1, placing shorter sticks, which do not affect visibility, and there are I1 choices for such placements. Each value is taken modulo 10⁻9 plus 7 to prevent overflow. Finally, dp n k gives the desired result. This approach is efficient with time and space complexity of O(n*k). This is the Java implementation of LeetCode problem number 1866, number of ways to rearrange sticks with k sticks visible. The logic mirrors the given Python solution, employing dynamic programming with a 2D array to calculate the number of ways to achieve the desired arrangement. Key differences include Java's strong type declarations, modular arithmetic using explicit casting for large numbers, and the use of Java's array indexing. The computed dp table supports iterative filling, ensuring efficient memory usage. To solve this problem, we use dynamic programming. First, we need to initialize a dp table with dimensions n+1 hx, k+1, and fill it with zeros. The base case is dp 0, 0 equals 1, which represents the one way to arrange 0 sticks with 0 visible. Starting with this base case, the initial table looks like this: rows represent the number of sticks n, and columns represent the number of visible sticks k. For the first step, we consider I equals 1 stick. If we want one stick to be visible, we can place the only stick in the visible position. So, dp 1, 1 is updated to 1, as it depends on dp 0, 0. This gives the updated table where dp 1, 1 equals 1 and the rest remain 0. Now, we move to I equals 2 sticks. If only one stick is visible, the tallest stick can be placed in the visible position, or we can hide it behind another stick. Using the recurrence relation, dp 2, 1 becomes dp 1, 0 plus dp 1, 1 asterisk 1, which evaluates to 0 plus 1 asterisk 1 equals 1. Next, for j equals 2, we want 2 sticks to be visible. Here, the second stick is placed as visible, so dp 2, 2 equals dp 1, 1, which is 1. This gives us the updated table, where dp 2, 1 equals 1 and dp 2, 2 equals 1. Moving on to I equals 3, with 3 sticks, we calculate dp 3, 1 by placing the tallest stick in the visible position or hiding it. This gives dp 3, 1 equals dp 2, 0 plus dp 2, 1 asterisk 2, which evaluates to 0 plus 1 asterisk 2 equals 2. For j equals 2, where 2 sticks are visible, we compute dp 3, 2 as dp 2, 1 plus dp 2, 2 asterisk 2, resulting in 1 plus 1 asterisk 2 equals 3. Finally, for j equals 3, where all 3 sticks are visible, dp 3, 3 equals dp 2, 2, which is 1. After completing the calculations, the final dp table for n equals 3 and k equals 2 looks like this: 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 2, 3, 1. The result is found at dp 3, 2, which equals 3. This tells us that there are 3 ways to rearrange 3 sticks such that exactly 2 of them are visible. Next, let's consider the case of arranging 4 sticks with 2 visible. We begin by initializing the dp table in the same way as before, with the base case dp 0, 0 equals 1. Then, we iterate over I equals 1 through 4 and j equals 1 through 2, updating the table step by step. For the case where I equals 4, we calculate values for j equals 1 and j equals 2 using the recurrence relation. For I equals 4 sticks and j equals 1 visible stick, we calculate dp 4, 1 as dp 3, 0 plus dp 3, 1 asterisk 3, which evaluates to 0 plus 2 asterisk 3 equals 6. This represents the 6 ways to rearrange 4 sticks such that only 1 is visible. Next, for j equals 2 visible sticks, we use the formula dp 4, 2 equals dp 3, 1 plus dp 3, 2 asterisk 3. Substituting the values, we get dp 4, 2 equals 2 plus 3 asterisk 3 equals 11. This means there are 11 ways to arrange 4 sticks with exactly 2 visible. The final dp table for this example looks like this: 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 2, 3, 1, 0, 6, 11, 1. The result is found at dp 4, 2, which equals 11. Finally, we consider the case of 5 sticks with 3 visible. Using the same approach, we calculate dp 5, 3, based on the values from the previous row. The formula is dp 5, 3 equals dp 4, 2 plus dp 4, 3 asterisk 4. From the previous table, we know that dp 4, 2 equals 11 and dp 4, 3 equals 1. Substituting these values, we get dp 5, 3 equals 11 plus 1 asterisk 4 equals 15. This means there are 15 ways to rearrange 5 sticks such that exactly 3 of them are visible. The dynamic programming approach allows us to efficiently compute these values by building on previously calculated results. Now, let's analyze the time complexity of the dynamic programming solution. The algorithm relies on 2 nested loops. The outer loop iterates over the number of sticks, from 1 to n, meaning it runs n times. For each iteration of the outer loop, there's an inner loop that iterates over the number of visible sticks, from 1 to k, resulting in k iterations for each n inside the inner loop. We perform constant time operations, such as a few additions, a multiplication, and a modulo operation, all of which are O(1). When we combine these components, the total number of iterations is n times k, and since each iteration takes constant time, the overall time complexity of the algorithm becomes O(n asterisk k). This is a significant improvement compared to a brute force approach, which we'll discuss shortly. Next, let's examine the space complexity of this solution. The main contributor to space usage is the 2D dynamic programming table, DP, which has dimensions of n+1 rows and k+1 columns. This means the table contains n+1 asterisk k+1 elements. Since each element in the table is an integer, and integers typically take constant space in memory, the memory usage of the DP table is proportional to its size. Along with the DP table, we also use a few integer variables for tracking values like mod, I, j, and the return value, each of which requires O(1) space. When we combine these, the overall space complexity is dominated by the DP table, giving us a total space complexity of O(n asterisk k). This makes the solution efficient in terms of memory as well as time.
To put this into perspective, let's compare the dynamic programming approach with a brute force solution. A naive approach to solving this problem would involve generating all possible permutations of n sticks and then counting the arrangements where exactly k sticks are visible. Generating all permutations has a factorial time complexity of O(n), and for each permutation, we'd also need to count the visible sticks, which adds an additional factor of n. This makes the overall time complexity of the brute force approach O(n), which is computationally infeasible for large values of n. In contrast, the dynamic programming approach avoids generating permutations entirely. By leveraging overlapping subproblems and the optimal substructure property, it computes the result in O(n*k) time and space. This is a dramatic improvement, particularly when working with larger inputs. Finally, let's consider the best, average, and worst-case scenarios for this algorithm. Unlike some algorithms where complexity can vary based on input characteristics, the time complexity here consistently depends on the values of n and k. This means that the best, average, and worst cases all have the same time complexity of O(n*k). To further validate this, we can look at the mathematical reasoning behind the big O notation. The nested loops iterate n times for the outer loop and k times for the inner loop, giving us a total of n*k iterations. Since each iteration involves constant time operations, the overall time complexity is O(n*k). Similarly, the space complexity is determined by the size of the dp table, which is proportional to n+1 k+1. These bounds are tight and accurately represent the algorithm's resource usage. One of the most common mistakes in this problem is misunderstanding the visibility condition. Remember, a stick is visible if and only if it is taller than all the sticks before it in a given permutation. Misinterpreting this rule can lead to logical errors and incorrect results. For instance, assuming visibility depends on a stick's position rather than its height relative to preceding sticks would fundamentally break the solution. Additionally, attempting to solve this problem with a brute force approach by generating all permutations of n sticks quickly becomes computationally infeasible due to the factorial growth of permutations. Instead, leveraging combinatorics or dynamic programming can significantly optimize the solution. Another frequent pitfall is off-by-one errors in indexing. When working with permutations or recursive calls, it's easy to miscalculate indices, which can propagate incorrect results throughout the computation. To avoid this, explicitly track indices and use well-defined test cases to validate your logic. Finally, neglecting base cases, such as when n and k are both 1, can lead to runtime errors or unexpected results. Make sure to handle these edge cases explicitly to ensure your solution is robust. Another issue to watch out for is ignoring the constraints of the problem. If you overlook the given input limits or fail to optimize for edge cases, your solution may run into timeouts or other performance issues. Carefully analyzing the constraints allows you to design a solution that works within the problem's boundaries. From an interview perspective, this problem is a great test of pattern recognition. You'll often need to identify combinatorial patterns, such as deriving recurrence relations or applying dynamic programming principles. Interviewers may also challenge you to optimize your solution, moving beyond brute force methods to incorporate mathematical insights like Catalan numbers or Pascal's triangle. It's also important to explicitly address edge cases during interviews. For example, if k exceeds n, the solution is impossible. When k equals 1, only the tallest stick is visible, and when n equals k, all sticks are visible. Finally, be prepared to discuss trade-offs in your solution. For instance, you may need to weigh the time complexity of a dynamic programming approach against its space requirements, explaining why your chosen method is the most appropriate for the problem. This problem connects to several related problems that can help deepen your understanding. For example, LeetCode 60, permutation sequence, involves generating permutations efficiently, which shares similarities with the task here. LeetCode 119, Pascal's triangle 2, combines combinatorics and recurrence relations, which are key concepts in solving this problem. Another related problem, LeetCode 296, best meeting point, focuses on optimization over permutations, and LeetCode 935, Night Dialer, is another dynamic programming problem that involves counting paths under specific constraints. If you're looking for alternative approaches to solving the problem, combinatorics is a powerful method.
By using mathematical formulas, you can count valid permutations directly, which reduces computation time significantly. However, this approach requires a deeper understanding of combinatorics and is not always intuitive. On the other hand, dynamic programming offers a structured way to solve the problem. By defining dp, n, k, as the number of permutations of n sticks with k visible, you can leverage the recurrence relation dp, n, k, equals dp, n1, k1, plus n1, asterisk dp, n1, k. This balances computational efficiency with ease of implementation, as it reduces the problem to O(n squared) complexity. Memoization is another useful technique you can apply, especially for recursive solutions. By storing intermediate results, you avoid redundant computations, which can dramatically reduce the time complexity. However, the trade-off is that memoization increases the space complexity of your solution, as you need to allocate additional memory to store these results. This technique is particularly effective when combined with recursive approaches, ensuring that each subproblem is solved only once and reused wherever necessary. By carefully balancing the benefits of time efficiency with the potential costs of increased memory usage, you can craft a solution that performs well within the problem's constraints. To wrap up, we reviewed how to solve the problem of rearranging sticks with visibility constraints. The focus was on efficient problem solving and understanding how constraints impact algorithm design. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!